We will be filling out a rather large table here. So we have 4 columns, but there's about 14 rows. So you want to make sure you have a fresh page so you can fit everything on that page. In this table, we will summarize the directing effects of substituents, so whether they are meta-directing or orthopara-directing. And our groups that we list here, the substituents, are listed in decreasing order of activation, and I'll explain what that means after we get some of these substituents written out. So our columns, we will have the substituent group, the name of that group, so this way we can communicate about these groups a little better. We have some naming review. The directing effect. And then whether they are activating or deactivating. All right, so there are our 4 columns. We are going to start with amine groups. So an NH2 substituent or an NR2, where the R groups are carbon chains, methyl groups, ethyl, etc. So we say these are amino groups or alkyl amino. The first group of substituents that we write are orthopara-directing groups. So instead of writing that in every single row, we'll write out a few substituent groups, and then in our table write that all of these are orthopara-directing. So the next one we'll write is an hydroxy or alcohol group. Alkoxy groups. So this is like methoxy, ethoxy. So an oxygen that's bonded to the ring, that's also bonded to a carbon chain. The next will be acyl amino groups. So in this group, we have a nitrogen that's bonded to the ring, bonded to one hydrogen, a carbonyl, and an R group. So this is an acyl amino. And by the way, the longer horizontal line that I'm drawing on the left side of each group, this is where that bond to the ring is. So you can imagine, here's the benzene ring, and we're thinking about how that NH2 group influences, or is a directing group, how that influences the product. I'm going to erase the ring though, so we don't confuse that for being part of the substituent group. Okay, so we added acyl amino, alkyl groups, so a methyl, ethyl, propyl, those groups are also orthopara-directing. Acyl oxy groups, so this is when you have oxygen and then a carbonyl. me zoom out a little bit. We have one more before we'll take a break and talk about the directing effects. And the last one is actually another phenyl group. Actually, we'll do one more. Let's add in the halogens. So fluorine, chlorine, bromine, and iodine. All right, all of the groups, so here we can see all of them. All of these groups that we've written down so far are orthopara directors. One thing you might notice about all these groups that, or most of these groups that you'll see is different in the meta directors is that for almost all of them, the atom that's directly bonded to the ring, so for our first row, that's the nitrogen, second row is an oxygen, etc. Those atoms have a non-bonding pair, at least one non-bonding pair. That non-bonding pair can donate electrons into the ring. And so that's true for most of our orthopara directors, except for the alkyl group and the phenyl group. But both of those are not, those carbons that are bonded are not lacking electrons, so they can contribute electron density, but not a formal electron pair. So all of these, I'm going to zoom out just a little bit more, are orthopara directors. So all the way from our amino groups to the halogens. When we discuss the mechanisms with orthopara directors versus meta directors, whether they are activating or deactivating will become more clear. But because these substituent groups can donate electron density to the ring, these we classify as activating substituents. So that's all the way from the amino group to actually only the phenyl. So the halogens are not activating substituents. I'll of course explain why that is. But what this means to be an activating substituent, we're going to zoom in to this column so I can write this note in here, is that reactions with substituted benzene substituted with one of these activating groups will occur faster overall than a non-substituted benzene. So that's what we mean by being activating. These substituents will cause the reaction to be faster overall than if the benzene was not substituted. Now, halogens are special. Although they have non-bonding electrons that can donate electron density and cause the product to be an ortho or para product, they're still highly electronegative. Let's see, we'll draw an arrow to halogens. So halogens are highly electronegative. There ends up being a really polar bond between the ring and the halogen. That causes it to be a deactivating substituent. I shorten electronegativity or electronegative with eneg, capital N. So halogens are highly electronegative, so there's a very polar bond. And again, when we go through the mechanisms, When we go through the mechanisms, this will become more clear, just so you have all the information here now. Okay, so these are all of our orthopara directors. Now we're going to continue the table and write out a few meta-directors. One thing you should immediately notice about the meta-directors is that electrons are being withdrawn away from where the ring would be. So for example, our first group are a bunch of carboxy groups. So let's zoom in again. So we're going to put actually 3 groups that look similar to this in the same row because they have similar directing effects. But you can see if you look at the carbon that's bonded to the ring, so that is directly bonded to that benzene ring, electron density is being pulled away from that carbon. So this is an electron withdrawing group overall, and that's why it has a different effect on the mechanism and on the observed products. So this is a carboxy. We have carboxamido. So it's the same except we have an NH2 instead of an OH group bonded to that carbon in the carbonyl. Or we have a carboalkoxy. Which has an OR group. So these are carboxy, carboxamido, and then carboalkoxy. So all have similar directing effects. Then we have an acyl group. So that's a carbonyl bonded to a carbon chain. Oops. We will add a sulfonic acid group. which is SO3H. But we can write that out as, that's the structure. Oh, you can't see that? That's the structure. All right, we have 2 more groups to add. One is the cyano or nitrile group, and that's a carbon triple bonded to nitrogen. And then the last one is the NO2 group, which we know is the nitro group. And I'll draw that out so we can remember what that looks like. We have really a resonance stabilized charged molecule, and I just drew 1 resonance contributor. Again, you can't see that. There you go. Down below. So we'll put these in parentheses. So we know that is the structure. This is the nitro group. Again, all of these are electron withdrawing groups. All of our electron withdrawing groups are meta-directors. So let me zoom out. We have all of our ortho-para directors at the top, and then all of these are meta-directors. So that starts at the carboxy group. And then all the way down to the nitro group. All of these are meta-directors. And then thinking about activating or deactivating, since all of the meta-directors are electron withdrawing groups, these we consider deactivating substituents. Now this includes the halogens for the reason we wrote down above. Although they have non-bonding electrons, they're very electronegative. So when thinking about deactivating or activating, that very polar bond pulls electron density away from the ring enough to be a deactivating substituent. And then that goes all the way to the nitro group, which is the most deactivating. And then just to have this a similar definition that we wrote, or that I wrote in blue above, to define what these deactivating substituent means. And that means that reactions with substituted benzene, when it is substituted with one of the deactivating substituents, these reactions will occur slower than a unsubstituted benzene. All right, now we'll use this table to predict the products of a bunch of different reactions given the starting material.